All right, welcome to chapter 15.2. This is where we're going to talk about any energy conversion and conservation. Now, we've already talked about different kinds of energy, but energy conversion is the process of energy changing from one of those forms into another. An example of that is this car right here. This car was actually hit by a meteor falling through the Earth's atmosphere. So a meteor came all the way from outer space, and it fell through the Earth's atmosphere, and it hit the back of this car. Now, when it was in the atmosphere, and before it came into the atmosphere, it had gravitational potential energy, and probably a little bit of kinetic energy as well. It had gravitational potential because it was raised above the surface of the Earth, and it had kinetic because it was moving. As it fell, it got closer to the ground, and more of that gravitational potential energy was changed into kinetic energy, thermal energy, heat, and electromagnetic energy, light. So a lot of the stored energy that this meteor had because of its relationship to the Earth's surface and the fact that it was raised above it was turned into kinetic energy, which is why it hit at such a high speed. But it was also turned into thermal energy and electromagnetic energy in the forms of heat and light from the air resistance of that object falling through the Earth's atmosphere. So this is a conversion from one kind of energy into many other kinds. And this happens around us all the time. We are always taking advantage of energy conversions. But even though one energy can be converted from one kind into another, it can never be destroyed. We can never just get rid of energy. We can only help it change its form. And this is called the law of conservation of energy. Energy cannot be created or destroyed. Energy doesn't come from nowhere. Turns out the amount of energy in the universe has been the same for the last 13.8 billion years, or the age of the universe. So the amount of energy that we have in the universe never ever changes. It always stays the same. But it can change from one kind to another. So if this is true, why is it that if you stop pedaling your bike, you'll slow down, meaning you lose kinetic energy? You think, okay, I'm losing speed, so I'm losing energy, but it has to be transformed into another kind of energy, according to the law of conservation. What is getting in the way here is friction. Friction is slowing your bike down, and that means as friction acts on the bike tires, the kinetic energy is turned into thermal energy. So if you take your hands and you rub them together really fast, you can feel your hands get really warm. And that's because you are taking the kinetic energy of your hands, and as you rub them together, creating friction, some of that kinetic energy is being changed into thermal energy. So changing into thermal energy due to friction is a very, very common process, and we see it all the time. Now, one of the most common energy conversions is when an object is in free fall, meaning an object starts at rest some distance above the ground and then is dropped or let go. In this scenario, the gravitational potential energy of the object that it has when it is being held above the ground will be changed into kinetic energy as it falls. That stored energy will lessen and lessen because it gets closer to the ground. And the kinetic energy will increase and increase because its velocity is increasing. It's speeding up the whole time. Now, a little bit of thermal energy is created due to air resistance, but it's so small that we can basically ignore the thermal energy, and we will ignore the thermal energy when it comes to calculations. Now, an example of this is a pendulum. And a pendulum is a really classic example of energy conversions. So if we raise a pendulum bob, that's what this little sphere at the bottom of the string is, some height above the ground, it has gravitational potential energy. It has energy stored because it's above the ground. And as we let go, gravity takes over and pulls it, and it starts moving, and it actually speeds up the whole time it's falling until right here, the amount of potential energy it had stored is turned into kinetic energy. So this is where the bob is moving the fastest. This is where it has the highest kinetic energy. Because once it passes this point, that kinetic energy turns back into potential, and it slows down until it reaches the same height on the other side. So the amount of potential energy we started with is fully transformed into kinetic, which is then fully transformed back into potential. So this bob will never move higher than it did when we dropped it. It will always move back to the same height. Now, yes, eventually friction will make it move to a lower and lower point, and eventually it will slow down. That doesn't mean we're destroying energy. It just means we're turning it into thermal energy, which is not usable for us anymore. Now, in order to calculate the energy before or after a process, like the pendulum, we need to apply the law of conservation of energy. So that means that the energy we have before a process is always equal to the energy after. In the case of an object falling, that means that the kinetic plus potential before equals the kinetic plus potential after. So let's do a sample problem so I can show you what I mean by this. So at a construction site, a 1.5 kilogram brick is dropped from rest and hits the ground at a speed of 26 meters per second. Assuming air resistance can be ignored, calculate the gravitational potential energy of the brick before it was dropped. So we know two things here. We are given the mass of the brick and we are given the speed of the brick before it hits the ground. So mass equals 1.5 kilograms and the final velocity of the brick is equal to 26 meters per second. Now, it turns out we do know one more piece of information here. It was dropped from rest. So if it's dropped from rest, that means that its initial velocity is going to be 0 meters per second. Now, as I showed you before, we have to look at the kinetic plus potential energy before and have that be equal to the kinetic plus potential energy after. So I'm actually just going to go ahead and copy this whole thing, and we're going to use it as a calculation for this problem. So extend the page, make this not transparent so you can actually read what it says. So if we think about this, the brick is being held at some height above the ground, right? But the brick is not moving until it is released. So that means that if the brick is not moving, it definitely has gravitational potential because it's at some height above the ground, but it does not have kinetic energy to begin with because it's not moving. Only moving objects have kinetic energy. Now, at the end or after the brick has fallen, it is on the ground. Now, right before it hits the ground, like the millisecond before it hits the ground, it's moving very, very fast, but it is not raised any height above the ground. What that means is it has kinetic energy, but it does not have potential energy. So we have now narrowed this down to potential energy before equals kinetic energy after, because it was not moving in the beginning and it was basically on the ground at the end. Now, if we elaborate this, potential energy is mass times gravity times height. We already know that from the last chapter. And kinetic energy is 1/2 times the mass times the velocity squared. And at this point, we're ready to plug some numbers in. So we know the mass of the brick. We know that the mass of the brick is 1.5, so we can put that in for our kinetic energy equation, 1.5 kilograms. And we know that it was traveling at 26 meters per second right before it hit the ground. So then we do that squared, and that is equal to mgh. But if we look back at the question, it's saying calculate the gravitational potential energy of the brick before it was dropped. So we are actually going to put this right back into PEG instead of mgh because we are trying to find the gravitational potential energy. We're not trying to find the height or the mass or acceleration due to gravity. We're just trying to find the total amount of gravitational potential energy. So then if you put this into your calculator, make sure you put it in the right way. It should be 26 squared times 1.5 times 1/2. And you find that the amount of gravitational potential energy this brick has before it's dropped is 507 joules. So we started with what we knew, and we used our conservation of energy equation, and we narrowed down when we have kinetic and potential and when we don't. And from there, we were able to use the equations for both of those to figure out our answer. Now, that's a pretty classic problem, but it turns out Einstein took the concept of energy a little bit further, and he came up with this famous equation, E equals mc squared, when thinking about energy. Now, in this equation, E is for energy, m is for mass, and c is for the speed of light. And what this is saying is that the amount of energy an object has is equal to its amount of mass times the speed of light squared. Or in other words, we can take mass and we can convert it into pure energy under the right circumstances. Now, that is a conversation for another day, so let me know if you want to talk about it in class. But for now, here is the homework, and please have this homework ready to turn in tomorrow.